Today we will cover the topic of ship resistance, lecture by Donghyun Won and also Rachel Ho, and then discussion led by Kisuke. So, any question? Other questions? No. Then we can move on to lecture by Won Donghyun.
Yes.
We're online. You can share your screen then.
Yeah. Can you see the screen?
Right. Go ahead.
Hello, I'm Donghyun Won, and today I'll discuss key concepts in ship resistance and powering. The topic of this lecture is about the resistance and powering of ships, which is crucial for understanding ship performance. So I will cover ship resistance and how these factors are predicted and measured, because these are fundamental in designing an efficient and powerful ships. So let's start by examining the intricate relationship between ships' dimensions, its carrying capacity, and the encountered resistance. The larger a ship, the more efficient it is in transporting goods, but this also brings a proportional increase in resistance. So we will look at how engineers and designers tackle these challenges, balancing size, efficiency in the complex equation of the ship design. And predicting ship resistance is a very difficult task. It's a field where art meets science. So where traditional methods like empirical formulas blend with advanced techniques like model testing and computational fluid dynamics. However, real challenges like varying sea conditions and diverse cargo loads add layers of complexity to this task. We will study these methodologies, understanding their strengths, limitations, and applications. So in general, the ship's resistance is predicted with the CFD simulation first, and then verified this result by testing and measuring resistance in miniaturized ship model. So here's a video of testing resistance with ship model.
매주 한 권씩 펼쳐보는 나의 도쿄 로망. 로망에 가까워지고 싶어서 가벼운 학습지를 합니다. 다채롭게 채우는 10개의 외국어 로망. 가벼운 학습지.
비디오 스크린이 안 보인다고. 쉐어링을 잘못했었어. 쉐어할 때 전체 화면을 하든지 아니면 쉐어할 때마다 네, 봅시다.
So As I mentioned before, the ship face various of resistive forces from frictional resistance, which dominates at high speeds, to wave-making resistance, which becomes significant in rough seas, which is with a lot of waves. Additionally, factors like eddy formation and air resistance play crucial roles. In the rear operation of ships, the dominant type of resistance experienced by a ship is typically a combination of frictional resistance and wave-making resistance. So let's look at more details of this resistance by understanding the resistance of submerged bodies of the ship. In ideal flow, skin friction is a dominant component of resistance, particularly at higher speeds. It arises from the interaction between the ship's hull and the water. However, in rear flow, turbulent flow is more frequent, as the picture below. So we should also consider the flow separation at the backside of the body. So at the front of the body against the flow is compressed by the submerged body moving forward. And the rear side of the body, wakes are formed with flow separation. So the pressure at the front is high and the pressure at the rear side is low. This pressure difference is significantly contributes to the drag. So understanding these elements is essential for optimizing hull designs and enhancing ship efficiency. The transition from laminar to turbulent flow is a critical factor in determining a ship's resistance. While laminar flow offers lower resistance due to its smooth, orderly layers, the more common turbulent flow increases resistance due to its eddies and vortices, which make friction between flow and the shape of the body. Since the turbulent flow can easily be formed at high speeds, power needed to operate the ship exponentially increases as the speed of the ship increased. So this understanding is fundamental in naval architecture, especially the ship, influencing the design and operational strategies of the ship. As the picture on the right side, with an optimal design of the ship head, turbulent flow can be alleviated. So the shape of a ship plays a crucial role in its resistance. Thus, various design aspects like the coefficient of viscous resistance, the wetted surface area, and the ship's velocity interact to influence the drag experienced by a vessel, should be considered in ship design. With the hydrodynamic of each geometrical design of the ship, we can minimize the resistance and maximize the efficiency. And here's an example of well-known resistance and related ship design to overcome this. The wave-making resistance becomes particularly prominent in large ships. The energy expended in creating and overcoming waves constitutes a significant portion of total resistance. While the ship moves forward, like in this picture, the ship continuously pushes the water with its head, and this makes the wave, which can cause the drag. So as the solution for this problem, the bulbous bows is widely used in modern shipbuilding. The principle of this design is to cancel the wave formed around the ship. But by making the ships like this picture in this slide, the wave which can has the amplitude exactly opposite to the wave can be formed. So with this design, the wave which caused the drag can be cancelled out. Then watch this video for details.
Have you noticed how a lot of ships have this strange protrusion at the forward end? It's a big lump of metal sticking out below the water, and we call it the bulbous bow. But it serves a specific purpose. In this video I'm going to tell you what it is for and why they are fitted. Looking at these different pictures, you can see the ships are all different sizes. And just like the ships, the bulbous bows are also all different sizes. They're all designed specifically for the ship in which they are fitted, and they're all designed to serve one main function. To understand a bulb, let's first consider this vessel which does not have a bulb fitted. As it moves through the water, a pressure wave builds up at the front of the ship. This increases the height of the water. The ship is pushing it ahead, but that water has to go somewhere. So what happens? It flows back down the side of the hull. It will keep flowing back down, forming this wave all the way along the side of the hull. Now the problem with this is it increases the drag of the vessel. It's in contact with a larger surface area of water, it's coming higher up the hull, the water is moving at an inconsistent speed because it's going up and down as well as along. This increases the fuel consumption of the vessel. We need to find a way to mitigate this wave. We can model this wave mathematically. On this graph I've plotted a curve of y equals sine x. If we think back to mathematics, we also know if we plot another curve that is 180 degrees out of phase with our initial curve, then they will actually cancel each other out. All you do is you add up each of the points along the curve, and the resultant is this line straight through the middle. If we could generate the same thing on a ship, we would be able to mitigate that wave that's causing all that drag. Let's now return to our original ship diagram. I've now taken it out of the water so you can see the shape of the hull underneath. If we zoom in on the bow area, because that's the area we're interested in, I can do a quick redesign and add a bulb and change the underwater shape. This is going to affect the way the water moves around the hull. If we think back to the original waveform, I can overlay it here in blue. This is the effect that the hull itself has on the water flowing around it. But we've now got this additional bulb at the front. So what I can do is I can overlay the waves generated by that bulb alone, and I'm going to put them here in red. Now you'll notice that these two waves are out of phase with each other. And for what we just went through with the maths, we know that those waves can cancel each other out if they're out of phase the correct amount. In this case they are. And what that does is that flattens out the waterline along the full length of the hull. It does mean you still get that slight uprise here at the bow, but along the majority of the length, the water is now flat. This has reduced the drag and it's reduced the fuel consumption. And this is the main reason for fitting a bulb. If we remember back to the start of the video, we saw that old bulbs are different. They're designed specifically to produce that wave 180 degrees out of phase to reduce the fuel consumption on their designed vessel. Anything outside of the design parameters, we're talking speed, loading conditions, hull size, the bulb will no longer work, and it would actually increase fuel consumption because it's an extra lump of metal that the ship is having to carry around. If it doesn't produce that useful wave, it's no longer any good. And that brings us to the end of today's
So therefore, choosing the ship powering method is important because with the right propulsion methods to counteract resistance, the energy efficiency can be maximized. From traditional diesel engines to modern gas turbines and electric propulsion systems in these days, various types of propulsion system has been suggested. But in these days, the importance of improving energy efficiency is crucial because of the global warming issues. So naval engineers in these days are focusing on developing the propulsion system with low emissions like gas turbines or fuel cells. And here's the details of each powering system. First, the diesel engines are widely used powering system because of its high efficiency and reliability. It can be also used in a wide range of ship sizes and types, but it emits pollutants and noise and a lot of vibrations and are generated during the operation. The gas turbine engine provide a lot of power while being relatively lightweight, and it has the quick startup time. But its fuel efficiency is lower than diesel engines, especially at lower speeds. It is also more expensive to operate. And the last, electric propulsion system has advantages in emissions and energy efficiency. However, the limitation in energy system storage, like batteries, and the cost of the batteries or fuel cells is still high. And there are challenges in the sources of the electricity. That's all I have prepared today. Thank you.
Okay. No question? And we may move on to Rachel's. Right. Rachel.
Hi everyone, my name is Rachel and I'm going to be talking about resistance and powering. So just going over a brief overview of what I'm going to be covering. In addition to what was previously lectured on this topic, I'm going to be talking about the historical background of resistance and powering, different resistance components and how that's comprised of, how energy and power estimation is used in conjunction with resistance components, and then finally how you use those different educated points to make an engine selection, and then predict resistance further accurately using computed methods, and finally, on a current level, how this is looking like in the shipbuilding industry. So regarding history, before the 1800s, there's only steam. Before the 1800s, there was only wind-powered ships, and following that, there was the development of the steamboat. So before this, the ships were reliant on wind. And as you can see on the right, I'm not going to get too much into detail about how the physics of winds work for different ships. But generally, the large point was that in addition to wind being a limiting factor for a lot of ships, there was also the limitation of only having wood construction. So the new problem that developed after steam power moved in is how can we effectively propel through a medium of water. Now, instead of only looking at the medium of air, we're looking at two different mediums at the same time. And in addition to that, the developments that came with looking into propelling through water was different materials for the hull. So steel and iron hull proved to be much more effective in moving through water, and not only through the hull, but steel and iron actually was slowly incorporated into shipbuilding throughout time. So we can not only look at the hull, but also if we talk about the supports or even the frame, such as the SS Great Britain, which is actually the first ship to have a steel hull, you can see how those materials were actually very crucial overall for the change in shipbuilding. And another additional development that came with looking through the medium of water was the screw propeller, which was more further developed through the Civil War. It was actually based off of the Archimedean screw, which was originally used as a pump, but was further developed for engine use for ships. So to start this discussion about different types of friction and how that has to do with using the air medium and the water medium, I'm going to start talking about surface ships. So the big point of this is that the ship is partially above water and partially below water. So looking at what part of the area of the ship is water wet makes a huge difference in regards to how we make an approach to optimize its speed to whatever specs that we need it to be. So the big resistance components that we're looking at are two, which is frictional and wave making. So frictional refers to overcoming the water viscosity so that the ship can effectively move, and which is more of the underwater part. And the wave making is overcoming the gravity. So as you can see through the diagrams here on the top right, there's something called boundary layer, which is effectively what is an attached idea with the frictional resistance. So in fluid mechanics, there's something called laminar and turbulent flow, and ideally you want something laminar, just as it basically allows the water to be less dragged and decrease the friction as the ship moves. And for wave making, like, as you can see on the bottom here, there's some diagrams of how that would look like as the boat cuts through the water. So on the top of bottom left there, you'll see that, and on the bottom right, you can see how the boundary layer moves around the ship, and the boundary layer is essentially the outline of water that happens from the resistance from the friction of the hull. And behind the ship there, if you look at the diagram, I know it's very small, but there is a wake, which is the water that's left behind. And therefore, altogether, these two make the largest components of resistance. And under wave making, there's also some residual, which is residual friction, which is caused by eddies, which essentially has to do with the contour of the ship and how that reacts with the water. But generally, when these calculations are made, air resistance is considered negligible. So the big points of this is that the surface, an ideal hull surface, will minimize frictional resistance. So that means that we want a smooth surface to minimize friction. And from that concept, you can also really think about the cleaning and the paint of the bottom of the ship. So there was a study conducted regarding barnacle settlements under the hull of the ship, and they found that it can cause an up to 10% increase in frictional resistance, and as well decrease up to 20% of the maximum speed of the ship. So that just goes to show how important it is to have a smooth surface. And while the surface will affect the frictional resistance, the residual resistance will be affected by the hull form. So how that is cut through the water and how that shape interacts with the water around it will define its speed. So for slow speed ships, generally the frictional resistance is 3 to 4 times more than the residual resistance, because it has to get over that initial static friction. But the high speed ships, when it's already in motion, they can become an almost equal amount. So for submerged bodies, this is regarding an example where we would only be talking about the underwater friction. So for a deeply immersed body, which is such as like a submarine, there's no wave making resistance at all. So therefore we would remove that component of resistance. And as I mentioned before, with laminar flow and turbulent, in an ideal fluid, the body experiences no resistance. So D.L. Almbert's paradox, to just briefly explain that, it's just a theory that talks about the limitations of fluid mechanics and how we engage with that, because with an ideal fluid, we often assume that it has no vorticity or no viscosity. And in that ideal fluid, we shouldn't have any resistance at all. But of course, that is starkly different from how it actually is applied in real life. So that's just a brief overview of how that's interrelated with that topic. So talking about where the energy is allocated, the large point is, this starting point is the propeller shaft, and at the end is trying to get to the propeller, and there's a loss of energy that occurs there. And as you can see through the diagram, there's multiple points in which that energy is lost and causes a decrease in efficiency of energy, but generally about 1 to 2% goes to shaft bearings and seals that are focused on keeping water from seeping in. And the big point of the propeller shaft to the propeller is to convert torsional energy into thrust, so moving a rotational movement into a forward movement. And generally, this comes to be around, in a really ideal condition, maybe 70% as the efficiency number. Further on energy, as I mentioned before, there's something called wake, which is what is behind the ship as the water moves around it. And if you think about it from a visual standpoint, that allows for a slower amount of water to be present behind the ship. And when the propeller operates in that slower water, it gives it an advantage called wake gain, which allows it to move a little bit faster and conserve energy. But on the hindsight, due to this wake, there's also a suction that occurs that reduces the water pressure on the stern and makes the ship work harder to make it move forward. So the difference between this ideal wake gain that's a benefit and a thrust deduction, which is a detractor, comes to a difference that's known as hull efficiency, which you can see the sign for it right there. And on the bottom there, that's another way to calculate hull efficiency, but it's utilizing W and T, which W stands for wake fraction and T is the thrust deduction coefficient. So if you multiply that with the propulsive coefficient, you get something called effective horsepower, EHP. And propulsive coefficient is a ratio between the horsepower and the thrust horsepower. And you can see there's multiple different ways to calculate this. And both of these efficiency ratios use different power measurements to also effectively conclude on the numerical values that they are. Okay. Okay. And another additional efficiency value that we look at is relative rotative efficiency, which can be multiplied with open water propeller efficiency, and in addition to previous hull efficiency to create the propulsive coefficient. So one of the biggest points why this is important to understand in shipbuilding is that when people design ships, they don't want it to be too fast or too slow. When it's too fast, it's a waste of resources as commissioned. And if it's too slow, then it won't reach the target in which it needs to be utilized for. So finding that ideal amount is what this topic is really focused about. As you can see, there's a little bit more description on how horsepower is calculated overall, but as I just talked about the effective horsepower, this can also be further brought into brake horsepower and shaft horsepower, which basically account for different parts of also within the ship. For brake horsepower, if it's diesel or gas, then that's how it's associated with. And shaft horsepower is if it's a steam turbine, and they are identical in diesel engines, but if it's a geared engine, the BHP goes into the reduction and the SHP is the output. As I mentioned before, I've just thrown a bunch of formulas overall, but generally these are different power definitions, and different ratios and combinations of these different powers will essentially make the different efficiencies as noted, and also those efficiencies can be manipulated to pull whatever quantitative number that you need from this. So a brief overview again with the diagram kind of showing which power definitions are relevant to what part of the ship, as well as their relevant units. This was the original slide regarding the engine selection procedure using all of this information, but I just kind of rewrote it so it's a little easier to read here. But essentially this process kind of combining all of the topics that I just discussed is, the first is to estimate the frictional resistance, as again mentioned, which is the friction with the water viscosity. And the second is estimating the wave making resistance. And then if you add the appendages, which is the additional things such as the eddies, you get all of these together to get the estimated effective horsepower needed. Then by dividing the EHP with the propulsive coefficient, you can finally get the delivered horsepower. And then if you account for the shaft losses and the brake losses as well, you get the final BHP as needed. And then you add something called a power margin, just accounting for real life instances that wouldn't be aligned with the ideal that we calculated. And then finally, we would select an engine or turbine that would match our specs. And as mentioned before, we don't want it to be wastefully fast, but we also don't want it to be too slow. So trying to find that sweet spot is what this procedure is about. So Froude's number is an essential component that has to do with calculating the resistance or estimating the resistance. So to simplify a really complex idea into a short lecture here, Froude's number basically was revolutionary because it described the scaling of resistance from a small model ship to a larger realistic ship in a non-linear way, and it accounted for it in an effective manner. And also another large important part of Froude's number that allowed it to be more effective was that it separated the resistance components of friction and wave making and added them following their separate scaling. And for Froude's number, as you can see at the bottom, there's a brief formula, and on the right you can see the graph. But generally, for Froude's number, you want to hit a critical point, which is when it is equal to 1. It's a transitional point between subcritical and supercritical, and when the potential and kinetic energy is balanced, and when there's the lowest amount of energy, specific energy, which is helpful essentially to decrease the amount of wasted energy that is going into making an ideal ship. But if it's less than 1, then that means the wave velocity is higher than the flow. And then this is more present in deep water with shallow currents, and supercritical is when it's greater than 1 and the inverse. And this is very much a concept very tied to like the critical, supercritical, subcritical. This is a concept that's very tied to fluid mechanics. But generally that's how it's applied to making effective estimations of larger ships. So this is something further on predicting resistance. So one of the big points of the textbook that we use for non-naval architects is that it's quite dated. It's from about 20 years ago. So when it described about predicting resistance from hull shapes, it didn't really have a lot of information. But I'm going to now speak to a research paper that was done within the last 5 years regarding not only technologies that have existed for predicting resistance regarding hull shapes, but also new technology that's been incorporated. So if you guys ever heard of FEA, if you're in engineering, it's finite element analysis. It's a very similar concept. Basically, there are different nodes on the hull shape, and you can simulate how it would react to different environments according to its shape. In this case, for shipbuilding, it's called EFD, which is experimental fluid dynamics, and CFD, which is computational fluid dynamics. And the research paper that I read about talked about the roughness impact factor. So that was essentially incorporating an extra variable of how the roughness was laid out on the hull, and how that additionally on a smaller scale affected this larger scale of the shape. So on the way end over there, that's the traditional different shapes that are looked at the hulls. And on the right here, this is the more custom parametric shapes that they made for their model in this specific research paper. And then also them talking about how they differently laid out the roughness on the hull. So these are some advanced topics that were briefly mentioned that I'm just going to briefly go over as well. So the hydrofoil craft on the top there essentially allows for less wave resistance, or even you could say friction resistance as well. It helps lift the ship out of the water. And it can be a hull or the wing that is the hydrofoil component that allows the ship to be lifted out of the water. And although the pros you can imagine from the idea of lifting it out of the water and decreased friction is that the ride can be very smooth, and there's more fuel efficiency as there's less fuel required to make it move and reduce drag. The problems with that don't make it highly adaptable is its cost, the different components required for its maintenance, and it's very sensitive to weight. doesn't do well in shallow or choppy waters, although it allows for a smooth ride and otherwise. And the pilot skills are important to make it effective. And then on the bottom there is air cushion vehicles, which also is a very broad amphibious division of shipbuilding, but it's also focused on decreasing resistance overall in the water. So this is just a brief snapshot of the marine engine market. As you can see, it's becoming something that's being more and more focused on, especially as I would say, as shipping increases, and as well as the fact that there's more of a focus on creating efficiencies with this. And then for my final slide, I just wanted to briefly talk about modern advancements in this area. So originally on this PowerPoint, they had something regarding development from CRISO on the bottom right here. I'm not going to play the video, but it's essentially the like pink magenta color. It's a K-cap, and it's something that's attached to the back of the propeller, which decreases the loss from the cavitation caused by the propeller through a hub vortex. And then on the I'll play the video in a second, but there's a new development called toroidal propeller, which was developed by MIT and some other folk, which is a very similar concept to the CRISO K-cap that was created, focusing on the propeller section and decreasing the loss from there. And the one additional interesting point I wanted to talk about was how wind power is actually returning. There is a common misconception that wind power is outdated or no longer effective, but as you can see from the list there's been a lot of movements regarding creating a wind power hybrid ship, especially with the oil crisis and a better technology regarding forecasting wind, and an increased focus on sustainability. This is something that's being re-explored in regards to ship resistance in water. And I'm just going to play this video, and that will be link, copy it. Okay.
코트를 벗지 마라고 하면은
This is a toroidal propeller. It gets its name from the blades, which are in the shape of a torus, which is often described as resembling a donut. However, these special donut-inspired blades are much more impressive than they first appear. In fact, they have proven their ability to more than double the propeller efficiency when used on a boat, which greatly increases speed and fuel economy. Not only that, but these propellers can massively reduce the noise of both drones and boats. In this video, we'll see how it does this and some examples of it in use. The physical difference between the toroidal prop and a standard prop is obvious when you look at them, but it is not immediately obvious why this has such huge benefits. However, if we look at these two operating next to each other, things start to become a bit clearer. Firstly, this is a comparison between a toroidal prop and a standard prop. You can see far less bubbles, known as cavitation, coming off of the blade tips, even though the blades are the same size and rotating at the same speed. This is because the toroidal prop generates less tip vortices, which can cause noise, vibration, and reduce efficiency. It is believed to do this because the vortices that would develop at the tips are instead spread across the whole blade. In this second comparison, we can see that the toroidal prop also brings in more surrounding fluid as it spins than the standard prop, as the die from further away is pulled into the blade. This gives a further increase in both efficiency and thrust. The two main toroidal propellers I've seen is the one from Sharrow, who have been focused on marine applications, and one from a research group at the Lincoln Laboratories within MIT, who have been focused on extremely quiet drones.
We came up with this initial concept of using this toroidal shape, this annular wing shape.
I think that's a good summary of the video. If you guys want to watch the video, you can do that. And that's the end of my presentation. Sources.
Oh. Right. We can move on to discussion session.
Okay. Hello, my name is Keisuke. And thank you for being here today. We're going to start about the presentation. Discussion part. Uh, So we didn't cover this in a presentation, but when it comes to ship resistance, we have basically the major thing is the water resistance, the fictional, residual resistance and fictional resistance and air resistance. Where it comes for air, it is in case when the upper part of the ship is conflicting with the air fluid. So we basically covered these three. And for discussion, I would like to discuss about the red part. So yeah, let's just first talk about this topic. So based on your comprehensive knowledge, which of the wave making resistance goes fast? Which of the ship goes faster? The longer wavelength or shorter wavelength? I guess it's really easier to consider about this answer if you deeply simulate the situation in your head. Does anyone have any idea for this? Go ahead.
I think the second one is the bigger wavelengths because it will have less impact on the speed of the ship than when they are shorter wavelengths.
Yeah, I think that's really correct. And I also received exactly same answer from the chat. It says the longer goes faster. And yes, it is. The slow speed is the speed of the ship is based on the resistance of the wave, and therefore the longer wavelength accounts for lower resistance, and therefore it has more higher speed in terms of longer wavelength. And I think we covered about this resistance part in a presentation. The drag coefficient is based on following equation, and this is called coefficient because the shape, the resistance depends on the shape of the material, the surface of the material, the attachment of the material. So let's go to next discussion. Guess the highest to the lowest resistance of the shapes. I think some of them were covered, some of them were not. So it would be good to share your opinion or share your idea. Which is the highest resistance, which is the lowest resistance. If you have idea, you could also chat on the Zoom.
I think that the highest would be like the cone, pole sphere, the cube, and the cylinders because they are not giving the end. The flow will just stop at the end, and they will have a lot of turbulence that will be created, which will make a lot of drag. Whereas the other will let the flow just go through, and when the two flows are going to meet each other, they will have less turbulences. So, for example, the streamlined body will be less, have drag coefficient less high than, for example, the whole sphere.
Yeah, that's pretty decent answer. And also, I also received answer from the chat. It says Q is highest and streamlined lowest. And yeah, you guys really doing really well. The answer is, oh my god, where's my cursor? The answer is the cube, and actually the short cylinder was the highest coefficient. And streamlined body and stream half body are the lowest and second lowest coefficient. The example from the air resistance, but we could also consider this for the water resistance, the wave resistance. The short cylinder, as we said, the short cylinder and the highest resistance, the stream body and stream half body were the lower resistance. I guess you guys are doing really well. Based on that, based on the shape of the streamlined half body, those shapes are usually applied to a ship shapes to lower the resistance. And I believe that maybe we got inspired or coincidentally inspired by the natural shape of the fish. The fish is from how do I say it? From the top of the body or from the side of the body, we can tell that the shapes are streamlined. They have lower resistance and they're able to run fast, swim fast inside the water. And of course, there are some fishes that doesn't shape like this, but most of the fish shaped exactly like stream body. So I think we apply this shape into ship to enhance the ship resistance. The next discussion is, can anyone guess evaluate the resistance? How to evaluate the resistance? I think we covered in the presentation how to evaluate the resistance. Yeah, we received some chat. It says, we make smaller tests and measure force on ship. Yes, the resultant force is linked to the drag coefficient, and
You can also use simulation like with CFD software to evaluate that.
Mm-hmm. Yeah. Those three are basically the process to evaluate the resistance, and I believe that you guys are really doing well. We have a lot of ways to actually evaluate, as we covered in a presentation. We could use computer CFD, traditional standard way. We basically make some samples and put into the pool and make wave and calculate the resistance. We could also do a regression based on the method. We calculate based on mathematical data and direct model test that is also shown in the bottom dynamic sets. I would like to cover these two red. One, let us propose some. Let's figure out what's the pros and cons of the following CFD and direct model test. So CFD is computer one. The direct model test is the bottom one. So by using the actual models.
The pros of CFD that they are less expensive like direct model test, and they make it possible, for example, to quickly change the shape of the pole that you want to test.
Mm-hmm.
But there are a lot of effects that you cannot predict. You have to make retests to be sure that your CFD was okay and to meet what they are the unpredictable flows. So that's why in the end you have to use direct model test, even if it's more expensive and more time consuming.
Mm-hmm. Yeah, that's true. That's true. There are some errors based on the calculation, so we need to also actual test. We need to have actual test. It would be better if we have the actual size of the ship and then do some experiments. But also, again, it's really time consuming and cost consuming. So we need to make a smaller module to have certain tests. Does anyone have any idea from Zoom chat? Any ideas? Pros and cons? I'll just wait for a bit. I got one response. It says CFD is more and more reliable, and implementing simulation is often more efficient than model tests. yes, that is one of the pros of having CFDs. But again, it is not always accurate. So we all, of course, need to apply the physical one as well. So let's just move. Oh yeah, I didn't build it up. So I think that's it for my discussion presentation. Thank you so much.
Right. We have a lot of time remaining, so I can use some additional explanation. Where is it? This is from Undeon, right? Undeon. This one. We are sharing? No. Okay. Sound is coming back. 왜 소리가 나한테 다시 돌아오죠? Okay. About the naming of residual resistance. You see, here you said viscous resistance is a frictional resistance is viscous resistance. The naming is a little bit complicated. Viscous. It is frictional. Then the other one is residual. They are saying the remaining one is residual resistance. So it's a total resistance is made of air resistance is a little bit different, but it can be separated out. So it be frictional and residual and air resistance. The name is coming from the model test. I don't know whether we are covering the model test. Maybe on 7th Thursday. But definitely we see that at the CRISO we'll see the model test. But when the fluid, he developed how to measure the resistance by using a Tony tank experiment. He found that he can separate out the frictional part from the remaining. That's why he developed the naming of frictional and residual. But you see that residual is bigger than frictional when the speed is high. When speed is low, frictional is more dominant. But when high speed goes on, the wave making resistance and residual, the eddy and wave making is much bigger, depending on the speed. High speed ship like a battleship. But the term is coming from, once again, when they start to measure by point tank experiment. So frictional resistance can be measured by using a flat surface calculation or experiment. Same area of wetted surface of the ship has same frictional resistance. So that can be calculated and measured separately. So if you see in the later stage of how they do the experiment and towing tank experiment and then calculate or measure the resistance, you will see that. So the naming is coming from the viscous part or the frictional part. The other ones, it's a remain. Okay, even though that is bigger than, it can be bigger than The other one, ion, still difference. Right. We see that from Rachel's lecture, we see a little bit on carbon. Let me show you. Oh, she. One or two? Two. Right. Where is it? Steel and iron. Steel and iron. You already know about what is the steel and iron difference, but you may not remember this. So I try to use you more on this. So carbon, steel, and cast iron. You remember this? This is a steel pipe, and this is iron cooking devices. So there you can find more on this. And then also you can see from this table, which one is simple. Maybe you can see. Right. So iron and steel, you can find this is alloy, and also you see that iron is a brittle, but steel can be bended. That is a one important difference. Right, so I want to show you a little bit more on this, and then the Rachel's one thing. Why we need to have a calculation of engine selection source, because for the shipbuilding company, and the owner, who can be a ship owner or a shipping company, they have a contract when they order a new shipbuilding. Right? The contract is saying there's guarantee of speed. Otherwise, there is a big penalty on this. But as your designer, at the beginning of the design stage, there is nothing, right? There is only requirement list. Shipping route and cargo and size, and also the contract says speed can be not less than 25 knots. That's why you need to have all the calculations and experiment are complicated. Very complicated. It is very tough calculation and estimation. But because of this guarantee, you need to have a little bit bigger engine than required, but not so much bigger, right? Because it's money, and also waste, as Richard said. All right, this is my additional ideas and comments. All right, on Thursday there will be a special lecture by a Navy officer, old Navy officer. So please come to classroom, not online, please, to help him have a more good feeling of speech. All right, see you on Thursday.